Okay, now we can start. So, attention please. So, now camera is working. So, Scott is going to present virtual aggregate testing. And this is your detailed explanation about your homework, where to get the files, how to run them. Some of you most probably did, but so Scott, the floor is yours.
All right. Yeah, this is the virtual aggregates testing. I'm sure the manual has been posted on D2L, and there's a link to a website where you can get everything you'll need for the assignment. Everything will be on this home page. Basically, what you'll need is the 2D packing, which will give you a link to the 2D packing portion of the assignment, which is all web-based. And then you'll download, under the download tab, the stuff for the 3D packing, which is an executable file that you'll get. I'm not sure about the other links. I think one of the links takes you to the paper you wrote, correct?
Mm-hmm.
And the other ones I'm not sure what are under those. So anyways, we'll start with the 2D packing. So just click 2D packing. It requires Java, so if you don't have Java, you need to install that. So I'll click run this time. I installed it earlier today. And you'll get a screen something like this. Oops. So you'll have your, once the program starts making the disks that'll be placed within a certain area, you'll see the particle size distribution along this graph right here. And then the bottom, you'll see different variables you can change. Number of disks, basically how many disks you want to place within your certain area. Reduction coefficient is basically the rate at which the particles is going to reduce. So, sorry, not the rate, but the size that it's going to reduce. So it'll start at a certain size, maximum diameter, and then reduce by that amount each step it goes through. The step of separation, that's how much it's going to reduce by. Or sorry, it's going to start packing particles at the distance from each other. So it'll start, say, a distance of 1 millimeter away from the next particle, and then as the packing gets more and more dense, that distribution is going to get closer and closer to each other. So that's your step of separation, which you can change the variables for that as well. Number of trials is how many times the program's going to try to fit a particle of a certain size within the area before it reduces down to the next size based on your reduction coefficient. So I think we're using 10,000. Yeah, so we'll use 10,000 for our number of trials. So it's going to try 10,000 times to fit a particle of a certain size within the area before it reduces down to the next size. Initial separation is how far the particles are spaced apart initially, and then as the steps move on, that separation will reduce based on your step of separation coefficient. So, and then the animation delay is just how long it takes to place the figure or the disk within the graph. That really doesn't matter as much. It's mostly just to help you visualize how the particles are being packed. So I'm going to change the animation delay to about 200 right now. That can obviously be changed, and it shouldn't make much of a difference in your calculations. Step of separation, I'm going to leave constant at 1.01. Initial separation, why don't we try 1.5 for now. And reduction coefficient.
You can make 1.1.
Great.
1.1, yes.
Okay. So for this, all you're going to do is say show 2D packing. Another screen will pop up like this. And it's good to have, you'll run into problems if you have your internet browser on full screen. So you want to minimize it and make it about half screen so that you can have both screens visible at the same time. Otherwise, it won't pack all the disks. The data will still be there, but you visually won't be able to see all the disks there. So it's good to be able to see both screens at the same time. And you're just simply going to say make packing, and it's going to start packing those disks within this given area. And you can see that as the disks are being packed, the packing or the percent passing chart is changing too. This time it only packed 50 disks, so you can see that since we had such a large initial separation, we have more spread out particles throughout. I'm going to do the same thing except we'll try 100 disks.
Can we remove this, make initial separation, say 1.1, say, so we have like a more close packing. And just pay attention for packing degree. Packing degree there on the top, already disappeared.
So now it's making 100 disks within this area. So basically, if the center of the disk is within this square, it keeps it. If it's not, it throws it out. And it's trying, so this is the maximum size particle. Tries 10,000 times to fit that particle within this area. If not, it goes on to the next, reducing the size by 1.1 and reducing the separation by 1.01. And then you notice right here, the packing fraction is about 63%. So 63% of that area right now is filled with the disk. And then your particle size distribution curve here. So D over D max, fit a few of those particles in. And then since we're only packing 100 disks, there's not really that much of a distribution in there right now either. And that's of course on a log scale. Should we try another one? Let's say initial separation of maybe 0.1. Now you can see that it's packing those particles much closer. And already we're